can. You obviously can't make the wind blow if it isn't blowing, but if you have a reliability concern, you can certainly shut down individual wind turbines or the entire wind plant. That's generally not economical to do so because the wind energy is the cheapest marginal cost on your system, but certainly nobody wants to compromise reliability. So if the wind is ramping up too quickly, you can feather the blades of the wind turbines and you can control the speed of that ramp. Down ramps are a little bit more challenging. You can't really control those, but other things can be controlled. Wind turbines in the U.S. now have low voltage ride-through capability. That was not the case in the past, where in the early days of wind energy, the system operator said, look, if the system crashes, I want those turbines to go offline, and I want them to stay offline until I'm ready for them. But with larger turbines and larger penetrations of wind, it's become important to have the wind turbines ride through those voltage dips. So modern turbines in the U.S. are designed and built so that they can ride through a low voltage. It's also technically possible to operate wind plants less than their full output so that the wind plant can actually provide regulation, short-term fluctuations that help the power system. And that's another question that comes down to the economics. Is it cheaper to do that, to essentially still with nearly free wind energy so that you have the ability of regulating from the wind plant, or is it cheaper to take all the energy you can from wind and use a gas unit that's on AGC for regulation? It's really a question that you have to answer by looking at the economics. Next slide, please. Can wind energy help make effective use of transmission lines? Well, really what's behind this question is a number of transmission paths, and certainly out here in the West, are loaded a pretty small fraction of time. And no surprise, the peak load period for the power system tends to be when the lines are more heavily loaded. Many other times during the year, the lines may not be all that heavily loaded. And with transmission in the West, typically you buy firm transmission, which guarantees you access to that transmission 8,760 hours of the year, whether you need all that or not. We did some work 3 or 4 years ago, 5 years ago perhaps, that looked at the path loading on a couple of key transmission paths in the West to determine whether or not you could inject a lot of wind energy on those paths much of the time, and we found that you can. And in part as a result of that work and other work going on around the U.S., the notion of conditional firm transmission was put out by the Federal Energy Regulatory Commission. That's now essentially a standard transmission product that can be utilized to access transmission that may not be available 8,760 hours of the year. And it may be that it's economic to do a little bit of wind curtailment if you've got a lot of congestion. And you think about building a transmission line to alleviate 20 hours a year of congestion. The economics probably don't really pencil out. It's probably cheaper to throw away a little bit of wind energy and avoid building the line. Next slide, please. So that's kind of the 10 FAQs. But, let me take just a few minutes here to talk about some things that increase the system's ability to take wind. One of the ways that we can get additional flexibility is by combining operations of adjacent balancing areas or control areas. The graph that you see here is an example of how that would work with wind. This is a snapshot of, I believe it's a day. This data is from the Minnesota 20% study. Now, that particular study was run under the assumption that by the study year, I believe it was 2015, the state would be operated as a single balancing area, not as several balancing areas. So Brendan Kirby and I went back and said, well, that's interesting. Let's take a look at what the impact of separate versus combined operations might have. Well, this is a fairly challenging time period here. And what you see on the graph, I think that we'll cut to the chase here, which is down at the bottom, the red part here. In one of those hours, part of the Minnesota system was ramping up 400 megawatts, so I've got to deploy generation to move up 400 megawatts in an hour. At the same time, or more than 400 megawatts, at the same time, another part of the state is experiencing exactly the opposite problem, and they're down-ramping 400 megawatts. And so this symmetrical red graph is showing the ramp savings that can occur by combined balancing area operations. And this is true if you've got wind energy in the system. It's also true if you don't have any wind energy in the system. So you can see that this 1 hour there was 400 megawatts of up and down ramp that could have been eliminated with combined operations. And what that does is that it frees up your ramping capability so that if you do have a lot of wind, you can use that ramping capability to help manage the wind, as opposed to having one guy chase the loads up while somebody else chases the loads down. Next slide, please. The next slide shows us that we can essentially talking about forecasting and how we can improve operations by not only getting better, more accurate forecasts, but making sure that the wind forecast is integrated into control room operations. It's provided in a timely manner. It's providing the kinds of things the operator wants to know. It may be beyond just what the wind energy production is going to be over a certain time period. It may also, there may be some kind of a risk component where the operator says, look, I want to have an idea of what is the probability of a high wind event that's going to cause the turbine blades to feather and the wind generation to go down. And even if you can't tell me exactly what time that's going to happen or if it's going to happen, knowing that it might happen is useful, because I can put the system in a position so that I can operate from basically a defensive point of view. So we see a lot of potential there. I think in regions that have hydro and pumped hydro, pumped storage, we don't, I don't think, have a really good understanding of how the hydro system can be operated within the existing constraints, which may involve fish and navigation and water deliveries, a host of other things. But it's not really clear how much additional flexibility is available to operate with higher penetrations of wind. And longer term, there's certainly going to be a lot of other interesting things happening on the power system. There are going to be new storage devices developed, and hopefully they can come in at a low enough cost to make them more competitive. Plug hybrid vehicles certainly has been something that's gotten on folks' radar screen. Hydrogen, other ways of looking at either storage or flexibility that could help with wind integration. Next slide, please. Actually, let me just take a minute to talk about these two. We have two really large-scale wind integration studies in process that we're managing here at the lab. One of them on the left is called the Western Wind and Solar Integration Study. We're looking at a pretty challenging wind scenario here. Up to 30% of all the electricity in the footprint, you see outlined in blue, coming from wind. And in addition to that, another 5% of the energy coming from photovoltaic, solar, and concentrating solar power. That study is in process right now. We're working with WestConnect. We are looking at the impact of combined balancing area operations. I think there'll be some very interesting things that come out of the study when it's finished later this year. The other study that we have going is the Eastern Wind Integration and Transmission Study. You can see the footprint of that study. It's most of the eastern interconnection, with few exceptions down in the southeast. This is also looking at, I think, 20% penetration scenarios of wind and a 30% penetration. That study is ongoing, and we expect some results later on this year. Brandon, if you want to just go to the next slide, and I think we can wrap up, and I'll take any questions. And keep going down here, I think two more. Those of you that may be involved or members of the IEEE may have seen two Power and Energy magazines, one in 2005, one in 2007. You can watch for one coming out at the end of the year 2009 that really take a look at wind integration, a lot of the things that I've talked about in a lot more depth than I've been able to talk about them. IEEE has a Wind Power Coordinating Committee, and there's a lot of effort going on with that. UIG, which I've mentioned earlier, it's a great source for integration information. And Brandon, if you want to show the pretty picture at the end, I'll be glad to take any questions that folks